Hello, in this video we are going to go over the solution of the problem 378, case the smallest element in a sorted matrix. Imagine that we are given a matrix like this one and all of the rows are sorted and they're increasing. For example, I have 1, 5, 9, 10, 11, 13, 12, 13 and 15. And also all of the columns are increasing. For example, I have 1, 10, 12, 5, 11, 13, 9, 13, 15. But beginning of each row doesn't have to be bigger than the end of the previous row. For example, here you see I ended this row with 13, but we are beginning next row with 12. Okay, so our goal is to find the case smallest element. It means that if I put all of these elements like this one in a sorted fashion, what is the case element? So here is 1, 2, 3, 4, 5, 6, 7, 8. So the result is 13. Okay, let's start writing the code. To solve this problem, we are going to use min heap. So first thing that I'm going to do is to import heapq. Let me name the number of rows with capital R and number of columns with capital C. So what is the number of rows? That is the length of grid. And what is the capital C number of columns? That is length of the first row. And also I need an empty list for my heap. I call that with a capital H, empty list. And then I'm gonna create my heap. But before doing that, what I'm gonna do is to define the length of the heap. So for doing that, so I just call that mini, and that is gonna be the minimum between the number of rows R and the K. K is the case element that we are looking for. For example, in this grid we have only 3 rows while we are looking for K equals 8. So the minimum is 3, so the size of the heap will be 3. The next thing that we are going to do is to go and look at the first element in each row and put that inside the list H. For R in range of mini, we do h dot append, and what I'm going to append to my heap is this. I'm going to put the value that I have here and its location. So I say grid R because that's the row we are, and we're always at column 0. What is the second element? That is R because that is the row we are, and column is 0. In that way I can put all of the elements inside the H, and let me just print that to see what we are doing. So I call it initial H, and let me run the code. So okay, this is H that we have. So I have number 1, number 10 and number 12. So you see I have number 1, 10 and 12, and each one has its own coordinate location 0, 0, 1, 0, 2, 0. Okay, next we heapify the H and say heapq dot heapify of H, and if I print that, I get exactly the same thing for this specific example. And the reason is that all of these rows are sorted. So as I added that one by one to the list, so the first element is the minimum. In fact, it is already heapified for us here, so there is no need to do that, but to be on the safe side, so I put that here. And there might be some cases I don't believe that would be the necessary, but it's still to be on the safe side, so let's keep heapify here. The next thing that we are going to do is to go for K steps forward and try to find the K's smallest element. So say for I in range of K, what I'm gonna do is this. I'm gonna get these 3 values out of the heap. Call it value row columns equals heapq dot heap pop and H. Okay, when I heap pop from the H, so for example I heap pop this element. So what I'm gonna do is to go to the one element to the right, which is actually the neighboring of that, and we know that is increasing, and add that to my heap. So let's do this. We say if column is less than capital C minus 1. What is capital C? Capital C is the number of columns, and so I'm just saying if I'm not at the last column technically, so let's heap push that. So we heap q dot h, and what we are going to add is this one, grid r c plus 1. So we are going to go one step forward in our columns, and then we say r c plus 1. I can at the end return value. Let's see what happens here. Okay, so we are going to get the value 13, as initially we saw that 13 is the 8 smallest elements. So let me print out some middle steps. Okay, let's go over the code again. So we said that we initially created this heap with the initial element of each row, 1, 10, 12. And then I'm at iteration I equals 0, and I go all the way forward for k elements. So iterations are 0, 1, 2, 3, all the way to the 7. And every time I go forward, I heap pop from the edge. So let's see what happens for the beginning. So for the beginning, the heap is this one. So at iteration 0, I'm going to pop this one, because that is going to be on the root of the heap, min heap. So this is our value that we just popped, 1. I go one column to the right, I go to 5. I add 5 to my heap, and automatically, because it's a min heap, that comes the beginning of the min heap. Next, I pop 5, and I go one column to the right to 9, and 9 is added to my min heap. Then I pop 9, then I pop 10, I add 11, then I pop 11 here. What should I add? I add 13. 13 at row 1, column 2, this one. But look what happened here. So because it's a min heap, it doesn't come to the beginning of that. 12 is at the beginning. So the next step to pop is 12. So I come and pop this one now, 12. And for 12, what is the next one? That is this one, row 2, column 1. That one is added here. Now I come and pop the next one from the heap, which is this 13. 13 at row 1 and column 2, this one. So can I add anything? No, there is no column. So I go for the next one. So 13, R2, column 1, this 13. Can I add a column? Yes, I can add 15. But consider that I'm at the end of the iterations. And here the value we just popped out will be our case smallest element. So I'm just going to return the value 13 here. Let's talk about time and space complexity. First thing that we did, that we created a heap, and the size of that heap was the minimum number of rows and the k that is given to us. So let's call that x here. So we say x equals minimum of r and k. And that is the number of iterations that we needed here to create that edge, initial edge that we had. And also because the size of that is x, when we do heapify, the time complexity of that is also order of x. So in this section, we have order of x for time complexity. For the next section, we have a loop that we had k iterations. So that is going to be here. And for each iteration, we have a heap pop, and the time complexity of that is log of x, because x is the size of the heap. And we might have heap push, for that one is also log of x. So as the result, the time complexity will be x plus k times log of x. And the space complexity is also order of x, because we created that heap that has x nodes. Okay, let's go over the solution again. So one naive solution could be to add all of the elements one by one to the min heap and try to find out the case smallest elements. But in this specific matrix, we had a characteristic that helped us a lot. And that characteristic was that all of the rows are increasing. They're already sorted, and columns are also sorted. So using that characteristic, we were able to solve this problem in a more efficient way and get this time complexity. Okay, this is the solution of the problem 378, and thank you so much for watching this video.